I am from Solace Systems. My name is Ken Overton. We build a data movement platform, i.e. messaging. I'm not so much here to talk about that as much as more about to share some of our experiences with these large distributed high volume systems that move lots of data around and some of the emergent patterns that we've found in that space. It's not so much in the vein of any secret knowledge or anything like that, but just some of the patterns we've identified, what we see recurrent. So when we speak of patterns, that's because there is never going to be one right answer for these kinds of systems. So instead, what we'd just like to show you is a kind of framework that we use to analyze and reason about these systems. And the types of parameters that we found were proving particularly useful in the analysis. And as well identify some of the questions to ask and some of the hazards to watch out for. So in the questions, of course, you have some of the obvious things in terms of your latency requirements. Does your application do batches? Do they do real time? How real time is real time for you? Is it seconds? Is it microseconds? Is it milliseconds? But also what type of networks you have. What are your throughput rates, your update rates? Do you send full images? Do you send deltas? What are your payload sizes? All of these kinds of questions, right? They go into the patterns, they go into the solutions, but there can never be one. It's not the same as a simple mathematical equation. You always have to fit the solution to the scenario. So the first of the parameters that we tend to look at, obviously, is latency. Everyone sort of assumes that lower latency is always better, but sometimes you engineer a solution for too stringent latency, you actually end up trading out some other things. So it's very important to identify just how latency sensitive you really are. If you do batch updates, how important is microseconds of latency to you? Probably not at all. Maybe seconds are often good enough, or milliseconds or micros. Some of the systems that would appear to be very similar up front in terms of latency turn out not to be the case. For example, algo trading engines have a very different latency profile than sports betting websites, just because of the WANs involved. Syncing a NoSQL database is very different from syncing a relational database system based on disk management. These sorts of questions are around the latency. So if you identify it sort of, I don't know if you guys are familiar with, some people call them spider graphs or radar graphs, but basically the less critical or less stringent tends to be at the center, and as you go out to the edge, higher and higher stringency across the different parameters. And we use radar graphs for these because they're not always completely independent axes, but they are sometimes interrelated. So the second parameter we often look at is network distance. This is physical network. So some of this is, are you transmitting data from one continent to another continent? Are you co-located with an exchange, for example? So feet make a big difference to you, whereas miles make a difference to somebody else. Is your application all constrained to a single LAN, a single switch within a LAN, or does it cross several different subnets and several different networks? Does it cross WANs? WANs are usually a very tricky thing to manage because you tend to have expensive, limited pipes. Not everybody has an OC 768 available to them with 40 gigs of network access across continents. So you always have to be careful of that and attentive to it in terms of how you measure and meter out what goes across the LAN and what doesn't. Additionally, you can employ things like compression, or you can decide whether it makes sense to spend the time on compression or whether it makes more sense to just send the full data. It often affects DR solutions or other forms of replication solutions. FX trading, global risk management, all of these things have both edges of the latency requirements because they'll be co-located with venues, but they'll also have to produce their risk across different global regions because you trade different currencies in different markets. The third parameter we often analyze is around the throughput, or the number of messages your applications are sending. Some examples, like at the two extremes, you could say point of sale terminals don't often send that much data. They tend to fan in, whereas market data applications, which are sending a new price, several hundred prices per second, crazy amounts. You run the gamut in between those. Risk management systems, order routing systems sort of sit in the middle. Market data streams or click stream analysis, they tend to be on the other edge, at the extreme. The fourth parameter is degree of distribution, and by that we mean the number of participants that are exchanging data. Are you exchanging data and the patterns they use? So are you exchanging it one-to-one to each and every individual in the room? Or are you fanning out the same data multiple times? Do you have to do something like you have a fanned out stream, but maybe you customize it along the way for the endpoint? Fanning out data, fanning in data. An example of fanning in would be sensors along a transportation network, or a train for positive train control, where all of these different sensors out in the field all have to fan in and sort of phone home, if you will, so that analytics at the base can actually possibly alter their behavior or at least perform reporting activities. The highest degree of distribution would be if you have lots of nodes organized in a full mesh where everybody talks to everybody. Obviously, an important characteristic to take into account when you're looking at a fully distributed system and how you manage data within that system. Message size, obviously another important one. Manufacturing, telemetry, these kinds of areas might have very large data sets, or they may be broken up into little small chunks where each delta occurs, gets a different message. Orders and trades are kind of in the middle. CDRs tend to be very call data records, different OATs reporting and these types of things. Batches obviously tend to be pretty large. When you move your systems from batch-oriented to real-time, you're looking at the possibility of altering the message size over time as you start rolling out things. Could change the profile of the platform that you use to distribute that data. There's very different stresses on your system based on the size and the frequency of the data. So frequency is related to size. For us, the guaranteed delivery factor is a very important parameter. And by that we mean, do you get updates or deltas to data such that an update for a message is coming right behind it, so whether or not you get each and every one of them is not so important as much as you eventually get all of the data. Market data is the typical end of that from the best effort point of view, which says, you know what, if I get the Microsoft stock price now, or I get it a millisecond from now, I can miss one in between, that's okay. Maybe I have a GUI. Maybe I have users viewing this on the screen. There's no point in updating that value in their screen 100 times. They can only perceive 5 changes per second, probably at the maximum. On the other end of that extreme, you have something like a sale or a trade or an order where every single message has to go through. In that case, any single point of failure has to be redundant. You can't tolerate that order not happening or that trade not being reported because dollars are on the line there. But this requirement can be deceptive because if, for example, if you have a system that is built on a request response paradigm, like a betting site often has, you don't necessarily need guaranteed messaging for that because your request response message exchange pattern sort of implies that. You could time out for example, your sender could time out on the reply, and if he doesn't receive it, just send it again. You have a built-in guaranteed protocol there, so you don't need to provide any sort of persistence underneath it anymore. So it's very important to sort of dig into the parameters and make sure that you actually really understand what the requirement is instead of just checking it off on the spreadsheet. So that's kind of the framework of the parameters that we find most important. Obviously, there's a lot more. The message format, your serialization mechanism, the protocol. Protocols can be important because a lot of times you'll have third parties or counterparties where they dictate the protocol to you. If you're in the telco space, you have to use diameter for a lot of the operational stuff. You have no choice. Diameter is the standard, and you will conform to it. You could have differences around how the data is structured or whether it is structured at all. That's just on the message alone. Obviously, networks affect things, whether you're on Wi-Fi networks, whether you're on very reliable networks, whether you're using TCP, whether you're using multicast, whether you're whether your infrastructure is robust enough to be able to handle failovers. At what level can you tolerate failures, and how or in what manners do you tolerate those failures? SLAs are very important in robustness because you have to define what a reasonable time frame is around failures, because you can't just say they will never happen. They will happen. It's a question of what do you do when they happen, and what's your time to recover? Which I think MBTF is, I don't know if that's a terribly familiar term. It just means mean time between failures. I guess it was too long to write. So this combination of all of these factors and parameters and questions all kind of yield design patterns as we've identified them. We've identified a few up front, but obviously there will be more out there in the field. So we try to categorize them sort of by the shape as they appear on the spider graph, radar graph, whatever you call it. And when we find a new one taxonomically, we'll add it into our list and see if there's a different, any different way to treat it or behave around it in terms of what we design. Now these attributes tend to correlate to each other, obviously. Some of them are correlated, some of them are semi-correlated, some of them are completely orthogonal. It all depends. But the trade-offs are always there, and you always have to be creative in how you address them. So that was kind of the framework that we use, and we can show you some of the patterns we've identified. We gave them each names here, but really they apply to a lot of different use cases, and sometimes it's kind of interesting to see where there are similarities and where there weren't, where you might think they are. The first use case that we run into a lot in messaging circles, obviously, is order flow. Also being in the financial services industry here in New York, we experienced a lot of this. In this, you see categorically, you see stringent latency requirements. I guess that going out to the edge here means that's a high requirement, not a high latency. The number of messages is always pretty high. It's actually not the highest out there, but it tends to be pretty high, whereas your degree of distribution, the number of nodes participating in a trading system, is often smaller than you might experience in other situations, because these are all very high performance nodes on this network that all do, possibly hundreds of thousands of messages each. So it doesn't take long before you'll saturate a network with systems like that. So you don't have lots of little tiny devices phoning home and sending in a message every minute or so. You have very few nodes all exchanging lots of data at very low latencies. The other interesting thing about this pattern is that you'll see that there's a fan-in, fan-out, but it isn't necessarily, it's not broad distribution, it's a bunch of little narrowcast distribution. And it is also a many-to-many in a lot of different ways. So an example with a market data distribution would be that you have one source of market data that goes out to several different destinations. But in an order flow environment, you tend to target your destinations, and you'll have multiple sources coming in with targeted destinations. So you'll see many come in and many go out, but in different unique fashions. Additionally, I'm sorry, I didn't mention the DR site on the side, so that adds in other complexities where you're transmitting data usually over WANs, hopefully over WANs. I know hurricanes never happen in New York, but they might in the future. The important characteristics then you need to watch out for, the hazards in an order system or a smart order routing is slow subscribers, which tend to degrade performance on networks. You have to make sure that your network can handle that. When everyone's spinning along, streaming along just fine, everything's great in a happy day scenario, but what happens when one of your applications crashes or one of your nodes crashes and it's in the middle of spinning up, but what happens to all of those events that need to be processed that are queuing up and waiting for it? Does the fact that you're queuing them up affect the other messaging participants? Does it affect the producers of those messages? These are the types of systems that it's very hard to design around those things. Slow subscribers are a chronic problem in the messaging space. Across the WAN, you also have the real-time sync problem. Do you synchronize data over to your DR site? Do you do it asynchronously or synchronously, I should say? Do you wait for the acknowledgement that's going potentially hundreds of milliseconds away? Because in that respect, your throughput of the events that you could accept would be the inverse of that. You've already throttled yourself to a maximum of 1,000 events per second, for example. So some of the applications that are similar that we find to the order flow use case are in credit card processing and e-commerce, which is, you would expect to be similar, right? They're doing commercial activity, they're engaging in bill payment or these kinds of financial translations. But you also see logistics scheduling with a very, very similar profile. Maybe it's a little bit less latency sensitive. Maybe it includes a little bit more WANs, and the edge endpoints are not as robust as the endpoints you might see in a trading system, for example. But your number of messages is very similar. Your latency requirements tend to look fairly similar. A very different pattern, though, arises when you look at manufacturing data synchronization. This is the case where you have manufacturing centers across the globe. You need to monitor and maintain those sites. You need monitoring within the site. You need monitoring across the sites. So you have very geographically distributed applications. 100% delivery guarantee requirement. This data cannot be lost. You can't just expect the next one to include the data that you missed. The data rate is very use case dependent. It's very hard to tell what your message rates will be. So kind of on the average, you say the data rates are less frequent than some other than more financial systems, but it could be very high depending on the use case. And same with the endpoints, obviously. So if we look at that type of use case, we're talking about different data centers, databases being synchronized, or sources of events being synchronized. They could be, you could have the event sources coming in from the manufacturing site. It will be fanned out to local databases while being distributed across to multiple replicas across different sites, and to analytics engines that run at different sites as well. So they tend to all fan out to each other. So you have a many-to-many distribution paradigm here. So obviously maximizing your bandwidth is very, very important. If you have a WAN link that provides you only 100 megabits, you can't run at LAN speeds or LAN throughputs. You don't have a 1 gig link here. What do you do when you have 1 gigs of data that you need to send over that WAN? Well, you need to compress it. You need to compress it before sending it. You need to be uncompressed at the destination. You need it to be fanned out. So you need smart buffering in there as well to accommodate the WAN. So if you get a spike of activity, you need that to accumulate before it goes over the WAN, so it can be metered out at whatever throughput the WAN can handle, even with your compression on. And finally, if you have this many-to-many distribution, it doesn't make sense to have 10 pieces of the same data go from, say, your Brazil manufacturing case to your Asia, Tokyo manufacturing site, when you could just send it once over the WAN and then fan it out at the edge. So all of these different tactics you can employ if you have control of the platform and you can control the use case or control the distribution. So some of the applications that have similar profiles in our experience are real-time risk management. They have smaller messages, or at least if the manufacturing use cases haven't chunked it up into little messages. Their latency requirements tend to be more stringent, but their guarantees are usually the same. And the rest of the profiles are very similar in terms of number of endpoints as well. Real-time financials, very similar to risk management, but it's a little bit different. And global inventory applications all sort of fit into this kind of profile. So moving on to something more wide area with a larger number of messages and a larger number of participants is sensor networks. And I guess we've labeled this oil and gas pipeline monitoring, but this could be anything where you have lots of sensors. This could be, for example, Homeland Security has sensors along highways to make sure that nobody's transporting nukes that they don't know about. So the sensors along those highways need to gather in the data from the cars passing by, identify the possible compounds that could represent nukes, and distinguish them from the ones that just represent kitty litter. So in this case, you have lots of different networks. You have Wi-Fi, you have satellite, you have proprietary networks, all kinds of different topologies there. You have a wide degree of distribution because you have lots of little endpoints with not a lot of computing power that all sort of fan in. The messages have to be small in this case because they're just sensing data and sending it out. They don't do anything else. But latency, well, if it gets here this second or the next second, as long as it gets there is fine. So, and I should say, as long as it gets there is usually fine. In some cases you need guarantees, but the guarantee is very idiomatic and case sensitive. Okay. This is kind of what the oil and gas pipeline or sensor network architecture looks like. Very different from some of the other networks we've seen in that it's a pure fan-in. Everything phones home. And then perhaps things will go back out, but you don't have a many-to-many type of distribution here. It's a many-to-one or many-to-few. In this case, you have to deal with unreliable networks. So your edges need software that is very robust in error handling. It can handle outages of the network or temporary outages, handle failover to peer nodes or those kinds of behaviors. You have delays that need to be accommodated between the different destination endpoint or analytics and databases. And finally, you need loading characteristics. So you need something, this is where your latency requirements are very important. How much batching is acceptable within your latency stringencies. Lower the latency, the smaller your batches can be, obviously. So that's kind of the profile for this. It looks very similar to the previous example that we looked at, except that in this case you just have lots and lots more messages, endpoints, distribution nodes. All right. So some examples here are power grid, smart grid, very similar type of sensor network, and transportation monitoring, another sensor network, but also retail point of sale. Now this is a little bit different in that maybe the number of messages will be fewer, but they all are edges that produce the events fanning in to the central location where you do analysis and recording of all of that information. It gets interesting when you can have real-time analytics working on that data, though, because then you start to turn the messages around. You can actually consume the messages and in real time affect the outcomes at the other end. So you can actually send interesting pieces of data back out to the edges and alter their behavior. So at a point of sale terminal, for example, if somebody swipes their card and they're a candidate for a particular type of, I don't know, special offer or something like that, you could potentially use something like this to analytically identify them, send out the appropriate data, and have your point of sale terminal behave accordingly. In a lot more serious scenario is what's called positive train control, where which is a law that required transportation train networks to be able to remote stop trains in the event that important hazards or problems were detected on the train. So from the control center, every train must be controllable. So you must be able to stop them in their tracks if necessary. It gets very interesting when you look at the type of tensions and the type of requirements around those transportation systems, the railway system. So for example, you'll have sensors on the trains themselves. You'll have sensors on the bridge that the train is approaching. So from all of that data fanning in, all these tiny little pieces of information that keep coming into the central repository, the central analytics engine, they can detect the speed of the train, the location of the bridge, and the wind speed on the bridge to determine whether they need to shut that train down because the wind is too high for the train to be allowed to go across. So this is very similar. Again, if we go back to that architecture, right? This is the positive train control example. Again, a fan in with potentially fanning back out to the same destinations. Different from the order smarter routing example, where you have many coming in, getting narrowcast out to many different destinations. In this case, we're still doing fan in and fan out to the same locations. So it's a much more controlled set of endpoints and set of nodes. In the first case, you would not want to have to nail up a connection to each and everything, because then when you get a full mesh, it's a crazy number of connections. So you want to have a broker in between. Something like this, they all phone into the broker. And they use the same connection to distribute the events back to those endpoints. It's a much more simple and controlled case. And I think this is our last example. Real-time sports betting sites actually can be different from the smart order routing in that it doesn't require as much stringency around those guaranteed delivery. And this is because of the request-reply scenario that I described. When I submit my bet to a sports betting site, I'm using request-reply semantics. So if my client can be coded to time out in the event of not receiving anything back from the site, and I'll just resubmit. The site obviously has to treat that appropriately and say, if it received that and processed it, it has to understand that this is the same message coming twice. So they'll have to deal with huge message volumes, event-specific volumes, where you can't just distribute this like the Super Bowl betting paradigm or the World Cup final. You can't just say the World Cup will be happening now over the next 24 hours. It happens when it happens, right? So they'll have huge volumes at some time, no volume at others. So huge volume, medium latency, depending. Internally, they'll have more latency requirements than externally facing. Medium level of guarantees in terms of which messages come in versus which messages get passed internally. And then the network and your internet mobile carriers become important, so your topology and the physical networks you're employing. So here's kind of the example for this. You'll have a message bus, or you'll have a central bus internally where all of these different applications are coordinating with each other. And then you have a last mile, if you want to call it that, out to all of the mobile and web customers to stream your odds and receive your requests. Now, the streaming of the odds is obviously not going to require any guaranteed messaging at all, right? That's just odds events that if you don't receive this one, or you received it and you already saw it, so one millisecond later, it's not a big deal if you see it again. In this case, within the LAN, I should say within the enterprise, low latency is very important. Externally, latency not so important. You'll also have clickstream analysis, so big data there, lots of loads into the data, and you'll have to window that appropriately. You'll have to act on it in a very timely fashion. Analytics is very important also in terms of the regulatory aspect of betting, making sure that nobody's trying to game the system or nobody's cheating. A lot of that type of activity is monitored and detected statistically in these clickstream and analytical engines. And obviously, you'll have huge connection counts externally. Because again, you'll have mobile applications, you'll have web browsers, lots of people logging in to do a very small amount of activity. Similar type of applications then, Facebook. Lots of edge nodes fanning in, not too much activity for each node compared to, say, an algo engine, which spits out 1,000 orders per second. But you also have less stringent latency requirements. But your distribution, obviously, out to the edges is going to be enormous. You have like just hundreds of thousands of connections at a time. The distance covered is also going to be similar because you have edge nodes, you have mobile browsers out wherever they are, across WANs and across Wi-Fi, wherever they are. So big WAN component, geographic component, latency, medium, market data distribution, can have high rates and high volume at spiky periods, as opposed to other more manageable systems in terms of the flow. So that is all of the use cases that we have covered. They cover a lot of the mesh, if you see it there, in terms of the spider graph. Maybe something there at the bottom that focuses on size of messages and less around, and with guaranteed delivery and high degree of distribution. Not sure what use case that would be. Maybe if you're replicating a database 1,000 times, that's about the only use case I could think of there. But for the most part, these use cases occupy a pretty good cross-section of all of this type of these set of parameters. So that's kind of how we see the patterns, how we've analyzed them, or how we've experienced them. And at this point, we could entertain questions, or you guys could all go out and have a cup of coffee. Yeah?
One particularly difficult problem we've seen is for cases where you have essentially a large message stream that you'd like to split into two because of different requirements for the different stuff in the message. But then you need some sort of guarantee that when you're processing this stuff, they're more or less together.
So you need ordering, but you want to parallelize the stream?
Imagine you're sending a trade down, just to take an example, right? But you want to separate the fact that it was a trade from potentially a large amount of reference data that trade goes with.
Right.
But by the time you're trying to look at that trade, you want the reference data to be up to date as well.
OK. So for example, one thing that would help, so first of all, if you're partitioning your environment along something where, say, the instruments that are being traded, so then you could have nodes that only process those instruments. That's obviously going to cut out a lot of the noise. The second thing that you can have is prioritization of different streams. What's interesting is to provide a similar use case I've seen is where you have a system that needs to accept orders, but more importantly, once it's accepted an order, it needs to get updates on that order. So as it approaches its volume maximum, it needs to actually have those priorities kick in so that it won't accept any new orders, but it will accept other types of messages on that same thing. So that's where prioritization, you could prioritize your market data above your trade data, and so you could perhaps vet them into the system when the trade data would have to come in behind them. That make sense?
Do you have like recommended solutions kind of based on those particular patterns?
Per each sample, yeah, there's definitely particular recommendations. So for a market data use case, obviously persistence is out the window. You don't want that. But maybe you like the idea of having something in place to avoid the slow consumer problems. So if you have big issues with slow consumers, then you need something in your platform that either reduces the amount of flow to those consumers or makes or separates them out so that they're decoupled from the others. So for example, if you moved from a multicast system to a TCP-based system, then those slow consumer problems in multicast where they knack back and start, you get these big sort of explosions across your multicast bus, can be potentially mitigated by decoupling them through TCP connections.
So you're looking at not just in the specific storage solution or the data solution itself, but the entire application, saying, kind of to his point here, you may throttle it somewhere upstream to is that all you're saying?
Yeah, well, I guess in my case, in this particular, that was just one example. But I'm saying that in that particular example, you could address the problem by just the choice of protocol that you're using, which layer of the stack you're going to address it in. So it doesn't necessarily have to even affect the applications at all, right?
How did you base those spider graphs extract? Where for which kind of data? Because is it something you decided on yourself, or is it an investigation? Or?
Yeah, it's our own people sort of typing in. It's what's the term I should use for it? Was entirely our own value judgments.
Oh, okay.
We say this application is very latency sensitive, so we give them a 7 out of 10. This one not so latency sensitive, we'll give them 2 out of 10.
Another question, I see mainly a bus solution in your patterns.
Yeah, that's
An option.
a distributed database can be a bus. Yeah, absolutely. Our experience is with buses, because that's what we tend to do, which isn't to say that there aren't other solutions that could engage with them. But as far as I'm concerned, a distributed database is a form of a bus, right? Because it unifies the way you onboard and egress data.
Yeah, it's only not there for queuing.
Right. Okay. What time is it? Okay, so there is no other questions. Thanks for your time. I hope you found this useful, and we will definitely be giving QCon the deck, and it'll be recorded, so if you guys need to go back to it after the fact, you certainly can.
Thank you.